So in today's video, we are going to continue with linear programming, and we are going to delve deeper into standard linear programs. So this is lecture 29, and I am Dr. Ranjan Ganguly. Now let us go back to the matrix form of the standard LP. So you recall that essentially this problem involves minimization of the function f of x, which is C transpose into x, where C and x are n by 1 vectors, n being the number of design variables. And this minimization problem is subject to constraints. The first constraint is Ax equals b, where A is an m by n matrix and b is a m by 1 vector. And also there is a constraint that x should always be greater than 0. So this essentially constitutes the standard linear program. Now, what do you do if you have a maximization problem? Well, if you have to maximize a function such as z or z here, you essentially minimize the negative of this function. So this will turn a maximization problem into a minimization problem. Now we see certain characteristics about the LP problem. The first is that all constraint functions are linear in an LP problem. The feasible region is therefore convex. The cost function is convex because it's also linear, and therefore the LP problem is convex. Now we are going to prove this using some very simple mathematics. So let's start with the fact that the points in the feasible region must satisfy the constraint Ax equal to b and x greater than equal to 0 for I is 1 to n. So essentially this particular set of equations or conditions creates what is the feasible region for the LP problem. Now let us say y and z are two different points in the feasible region which satisfy the constraints Az equals b, Ay equals b, where again the non-negativity constraints apply to both these variables. Now to prove convexity, we need to prove that if a point lies on a line connecting y and z also lies in the feasible region, then the LP feasible region is a convex set. So what we are going to do is that we are going to create a general point which lies on a line between y and z and see that this point also lies in the LP feasible region or not. So let's keep these three equations in mind and these three conditions in mind here and move to the next slide. So a point on the line segment connecting y and z is given by this formulation: alpha y plus 1 minus alpha into z. So this alpha value is between 0 and 1. Now let us take the equation Ax equals to b and plug this particular point into Ax equal to b, which we do here. So we have put this particular alpha y plus 1 minus alpha into z in lieu of x in this equation, and then we expand this out. So this is the expansion, further expand this out, and then we get b here. Now here I have used the fact that Ay is b and Az is b. So these two from the previous slide, and therefore this new point which lies on the line segment connecting y and z also satisfies the constraints in the feasible region. So essentially it satisfies A into the point equals b, and then we will see that it should also satisfy the non-negativity constraints. So that we'll do in our next slide. Now we see that alpha is bounded between 0 and 1. Therefore 1 minus this number, which is between 0 and 1, is also going to be bounded between 0 and 1. And you can check out by taking the extreme cases of the situation here. If this is 0 or this is 1, then this is essentially going to flip from 1 to 0. So essentially with this knowledge we can conclude that this new point will be greater than equal to 0 because all the z's are greater than equal to 0 and all the y's are greater than equal to 0. Therefore, if these numbers are also positive, then this new point also satisfies the non-negativity constraint and therefore it lies within the feasible region, therefore proving convexity. So we can say that this point between y and z satisfies all the requirements of being in the feasible region, and the feasible region is therefore a convex set. From this we can get the fact that the solution to the linear programming problem lies on the boundary of the feasible region. Now to again qualitatively think of this situation, if we look at the function here f of x and we use our calculus based thinking to find the unconstrained minimum, you would get the gradient vector would be 0 and therefore all these constants c1, c2 to cn will be equal to 0, which essentially means the function is non-existent and therefore we can say that this function doesn't really have a proper minimum point. So there is no unconstrained minimum point for a linear function, and therefore a linear programming problem must have constraints to have a useful solution. Also, the solution of a constrained LP problem must lie on the boundary of the feasible region. And this is easy to see graphically. Let us consider a situation where you have certain constraints. So there is one constraint g1x, there is another constraint g2x, and then there are the two non-negativity constraints on, say, these variables x1 and x2. So essentially this trapezoid here constitutes the feasible region. Now if fx is the function you are trying to minimize, this function has a certain value along this line, different value along this line, different value along this line, and so on. So essentially you can keep going down here or up here and there will be so many possible values of this line, and you can see that there is going to be no minimum point as such because these values are going to keep changing. But because of the presence of this feasible region, this line is going to come to some point, maybe it's here or it's here or it's here, some of these points here, and within this feasible region there is going to be a particular minimum point, and also we can see that that minimum point would lie on the boundary of this particular feasible region. So that is a very important part of an LP problem, in that the LP problem has a solution because of constraints. If constraints are not there, it really is not bounded. So we see that any optimal solution for a typical LP problem must satisfy the constraint Ax equal to B, and typically A has full row rank, which means that essentially the rows of A are linearly independent. Now if A does not have full row rank, you can have two types of situation. Your constraints may be inconsistent or redundant. Now if you have inconsistent constraints, the problem has no solution. The feasible region in that case is a null set and there is no extreme or vertex point. Redundant constraints can happen if two of your constraint equations are essentially linearly dependent, or you can visualize them as parallel. And therefore, if you remove the redundant constraint, the problem once again becomes okay, and you can then solve that particular problem. Now, there are few possible cases which can happen because of the values of m and n. Recall that n is the number of design variables and m is the number of constraints in the problem. So we also presume that these constraints are linearly independent. Now, if m is equal to n, essentially you have a set of simultaneous equations for which you can solve. And if you solve this, the objective function is not really relevant because you get the solution from this equation. Now, this is an interesting trick problem which can be set in tests or exams for an LP, that if m is n, then the solution is simply governed by the constraints. Now, in case this happens, the feasible region is obtained by solving the equation Ax equal to b, and it will contain one point if the xi's are all greater than equal to 0, or it will be a null set or empty set if any of the xi are less than 0. So always remember that the design variables must be positive for an LP problem, or to put it more precisely, must be non-negative. So we use the word non-negative because it can be 0, but it cannot be negative. Now, if m is greater than n, there may be no solution in most cases. This is kind of a least square type of problem. Now, the only case where this problem becomes useful and the objective function f of x can come into play is where m is less than n. And this leads to multiple possible solutions in a well-defined feasible region, and from here you can find the optimal solution for the problem. So essentially m is less than n is what you are looking for. Now, to write this important fact out, we can say that the number of constraints m must be less than the number of design variables n, and we seek a feasible solution which minimizes the cost function. So very frequently in optimization, as far as linear programming is concerned, the word cost function is often used in lieu of the objective function, and that is because many of the problems in linear programming come from a business perspective, so some cost minimization may be going on. Now let us define a few terms which are widely used in linear programming, starting with the vertex point. A vertex point is a point on a set that does not lie on a line segment joining two different points on the set, and it's also known as an extreme point. So that's a basic fact to remember. It doesn't join 2 points on the set. Now, pictorially you can see, for example, if we have a boundary of a polygon, if I take any 2 points here, I can draw a line between those 2 points. But if I choose a point at one of these vertices of the polygon, then I cannot join a line on 2 points. So essentially these extreme points are known as vertex points of a typical polygonal geometrical shape. Now at the extreme, if you have a circle, all the points lying on the circumference will be vertex points. But typically in linear programming, we deal with lines, and therefore polygons or multidimensional polygons are the geometrical figures to keep in mind. Some more important LP definitions. Feasible solution. Feasible solution is a solution of the constraint equations Ax equal to b, and remember then there are m of these equations, and also these solutions must satisfy the non-negativity constraint. So these are all the feasible solutions for the problem. Now a basic solution is a solution of this equation Ax is b obtained by setting the redundant n minus m variables to 0 and solving the equations for the remaining variables. So n minus m variables set to 0 are called non-basic. So one way I remember this is, say, non-basic are null, so essentially 0. So we take n minus m variables and set them to null, and these are the non-basic variables. So n for non-basic, n for null. The m remaining variables are called basic variables. Basic feasible solution. So this is a basic solution satisfying xi are greater than equal to 0, I is 1 to n, And a degenerate basic variable happens if a basic variable has zero value. Degenerate linear programs can take place when there is a redundant constraint. So you always need to formulate a problem properly such that you don't have such redundant constraints. And optimal solution is a feasible solution point minimizing the cost function, and this is called the optimal solution. So this is generic definition which would apply to both linear and nonlinear programming. The optimal solution has to be a feasible solution. That means it must satisfy the constraints. And of course, it should minimize the cost function because that is the practical problem you are trying to solve here. There is also something known as a convex polyhedron, and this happens if the feasible region or the constraint set for the LP problem is bounded, then it is called a convex polyhedron. So essentially, like the typical trapezoidal figure I drew for a two variable problem where you get a trapezoid, you extend it to n dimensions and then you start looking at this particular geometrical figure which is called the convex polyhedron. The basis is a definition which means the columns of the coefficient matrix A of the constraint equation Ax equals b corresponding to the basic variables are said to form a basis for the m-dimensional vector space. So essentially these are some of the basic definitions in LP which we will be using widely, and in the next video we are going to discuss how to get these basic and non-basic solutions for the linear program and how these can let us calculate some of the optimal solutions for a typical linear program. So this is a straightforward method to get solutions for these kind of problems. And after that, we can go on and look at the simplex method and the two-phase simplex methods, which are better or faster ways to solve this particular problem because you don't need to calculate all the basic solutions and so on. So I will terminate this video here, and this is the end of lecture 29, and I will see you in my next video.